Welcome back to Basic Electronics. In this class, we will continue with the shift register. We will look at a bidirectional shift register. We will also see how a parallel transfer between two shift registers can be implemented. We will look at how parallel in serial out data transfer can be achieved. Next, we will see how shift registers together with an adder can be used to multiply two binary numbers. Finally, we will start with a new topic, namely counters. So let us start. Let us suppose now that we have two shift registers. This A3, A2, A1, A0 is the first shift register, and B3, B2, B1, B0 is the second shift register. And what we want to do is to transfer the data which is in this first shift register into the second one. So that is easy to achieve. What we need to do is to connect this A3 as the D input of this B3 flip-flop, A2 over there, and so on. And now, after the active clock edge, the contents of the A register will be copied to the B register, because this A3 would show up as Q here, which is B3, A2 will show up as B2, and so on. So that is a very easy operation, and it is represented schematically over here. The shift register that we saw earlier was shifting data from left to right, but we can also make a bidirectional shift register shown here, which can shift data either from left to right or from right to left, depending on the value of this input called M or mode. When the mode input is 1, then the data gets shifted to the right, and if it is 0, then it gets shifted to the left in that direction. So let us see how this works. Let us take M equal to 1 first. In that case, what happens is this M bar is 0, and the output of this AND gate is 0, and essentially D is then the same as this input here, and similarly this D is the same as this input, etc. And then you will notice that we have exactly the same connection that we saw in the earlier example, and that is the shift right operation. With each clock edge, the data will shift from this flip-flop to this one, from this to this, and so on. What about M equal to 0? If M is 0, then the output of this AND gate is 0, and then this D in that case is the same as Q1, and similarly we will find that this D1 is the same as Q2, D2 is the same as Q3, and D3 is the same as DL. So that is the connection that we are talking about now, and with an active clock edge, this DL gets loaded into this flip-flop. Whatever was Q3 will now come here, whatever was Q2 will now come here, and so on. So in summary, with M equal to 1, we have the shift right operation, and with M equal to 0, we have the shift left operation. Let us consider a binary number 1101 here, and see what happens to it when we perform a shift left operation. This number is 1 plus 4 plus 8, that is decimal 13. This one has a weight of 2 raised to 0. This one has a weight of 2 raised to 2, and so on. And now let us see what happens when we shift it left. And here is the result of the shift left operation. This entire number has got shifted by one position, shifted left, and this 0 has got padded over here. Alright, the new number now is 2 plus 8 plus 16, that is decimal 26, and that is of course twice the old number 13. And this is not surprising because if we consider this bit, for example, its old weight was 2 raised to 0 and its new weight now is 2 raised to 1, that is twice the old weight. This one had a weight of 2 raised to 2 and now it has got a weight of 2 raised to 3, twice again, and so on. So therefore this entire binary number has got doubled by shifting left. So in conclusion, the shift left operation is equivalent to multiplying the binary number by 2. And similarly, shifting right is equivalent to dividing a binary number by 2. For example, if this was our original number and we shift it right to get this number, then the new number is half the original number. Now the question is, how do we implement these operations? These shift registers are available commercially as ICs, and we have already seen how to load a given number such as this one into a shift register, and we have also seen how a shift left or shift right operation is performed on a shift register. So we have discussed all the relevant mechanisms. We just need to put it all together and achieve these operations. Let us now look at multiplication using the shift and add process. And here is an example. 1011, that is decimal 11. That is our number A, A3, A2, A1, A0. A3 is this and A0 is this one. So A0 is the LSB, A3 is the MSB. Here is our number B, and that is decimal 13, and we want to multiply these two. So this is our multiplicand and this is our multiplier. Alright, where do we begin? We look at the LSB, that is 1. So we multiply the multiplicand by the LSB, and in this case it means we just reproduce this number as it is, 1011. Next we look at the next higher bit, and that is 0, and when we multiply the multiplicand by 0 we get 0 0 0 0, and that is what we write over here, and we have to shift it left because that gets a higher weight. So therefore there is a 0 coming in from the right here. Now a comment about the notation. This Z is actually the same as 0, but we use a different symbol Z to denote zeros which are independent of the numbers being multiplied. So this Z is always going to be 0 no matter what these numbers are. After that we add these two numbers, and that is the result. Next we look at the next higher bit, that is 1. So we reproduce the multiplicand, and now we shift it left 2 times, and therefore we get these two zeros here. We add again, then we look at the last bit, the MSB, that is 1. Therefore we reproduce this multiplicand again like that and shift it 3 times. So we get these 3 zeros here, and then finally we add these two numbers to get our final product, and that is decimal 143. Let us see how this method can be implemented. We start with two registers, 4-bit registers, register 2 and register 1. This is going to be our LSB, that is going to be our MSB, and we initialize both these registers with all zeros. Alright, now step number 1 is to load 1011, the multiplicand, this one, in this other register, since B0 is 1, and now we are going to add these two 4-bit binary numbers to get this result here, and this binary number is simply going to be copied to this part. Alright, so we have got 1011. In this case, of course, these are all zeros, so we have the same number over here. That is the result of the addition. Next we shift this result right by 1 position, So this number 1011 has appeared here now, 1011, and 10 has got padded from the left. Alright, now the next bit, since B1 is 0, we load 0, 0, 0, 0. We are talking about this step now. And now we are going to add these two numbers. And now you see that this corresponds to adding these two numbers here. And this one is going to get added to this 0. That is anyway happening because this one is simply going to get copied over there. Alright, so that is the result of this addition. And we keep repeating this process until we reach B3. So next step, shift right one bit. So this 0, 1, 0, 1, 1 has come here, 0, 1, 0, 1, 1. 1, 0 has got padded from the left. Now we load 1, 0, 1, 1 since B2 is 1. That corresponds to this step here. Add, shift right, and finally we load 1, 0, 1, 1 because B3 is equal to 1. That is this step here, and then add and shift. So that is our final result, and that is indeed the same as this number here. Let us look at this circuit and try to figure out what it is doing. We have 4 JK flip-flops and they're all positive edge triggered. Here is the direct set input SD. This is the direct reset input RD. And what we notice is that although we are using JK flip-flops here, we are really using them as D flip-flops, because you see that J and K are inverse of each other in each of these cases. We have 0 here, 1 here, we have Q3 here, Q3 bar here, Q2 here, Q2 bar here, Q1 here, and Q1 bar here. So although these flip-flops are JK flip-flops, the functionality is like that of a D flip-flop. So essentially it's a shift register that we are talking about. Alright, now let us look at the connections. The clock is common to all of them, and the clear input is also common. That is going to the direct reset input of each flip-flop. Now to SD, we are connecting this variable called load and it with some other variable here. That variable is A3 here, A2 here, A1 here, A0 here. And A3, A2, A1, A0 represents a binary number. And what we are going to do is to load this binary number into these flip-flops to begin with. These are the signals being applied. A single pulse here for the clear signal, single pulse for the load signal, and this clock signal has been derived from a free running clock and some logic. So the first pulse starts here and there are a total of 4 clock pulses. Alright, now let us see how this works. At this time we have load equal to 0, so the output of this AND gate is 0 and so are the others. So therefore SD is 0. The clear input is high, so therefore RD is 1. So we have SD equal to 0 and RD equal to 1, and that will clear the flip-flop. That means Q3 will be made equal to 0, Q2, Q1, Q0 will also be made equal to 0. After the clear pulse, the load pulse comes along, and let us look at the situation somewhere here. So the load signal is 1, clear is 0. So all the RD inputs are 0 now. This is 1, so the output of this gate, that is SD for this flip-flop, is equal to A3. Now let us take two situations. A3 equal to 0 first. So that means we have SD equal to 0 and RD equal to 0. So nothing is really going to happen. The flip-flop will work normally. Its output, if you recall, is already 0, and since there is no clock edge yet, the output will continue to be 0. So that is the situation if A3 was 0. Now consider A3 to be 1. In that case, SD will be 1 and RD is 0. So therefore, the flip-flop output Q3 will get set to 1. In other words, if A3 is 0, then Q3 would be 0 at this time, and if A3 was 1, then Q3 would be 1. So this bit here is simply getting loaded into this flip-flop, and similarly A2 will get loaded here, etc. So this entire binary number has now got loaded into this shift register. Alright, now the clock pulses come along. What happens when the first active edge comes? This 0 will get transferred to Q3. Whatever Q3 was will go to Q2 and so on. So that's a shift right operation by one position. And with each additional active edge, the data will simply shift right one more time. So that is how this circuit works. To summarize, all flip-flops are cleared in the beginning with RD equal to clear equal to 1, this part, and SD equal to 0. When load is equal to 1, this part, SD equal to AI, that means A3 or A2 or A1 or A0, and RD is 0, that means the binary number gets loaded into the shift register. And subsequently, with every clock pulse, the data shifts right and appears serially at the output Q0 over there. So first this A0 will appear at Q0, and after that this A1, which has got loaded in this flip-flop initially, will appear at Q0 and so on. And this corresponds to parallel in serial out data movement. Let us now look at this schematic picture showing this parallel in serial out data movement. What is parallel in? This is our data A3, A2, A1, A0, and that is getting loaded parallelly into these flip-flops like that. Alright, so that happens in this phase, and now the clock pulse comes along, the first clock pulse. We're going to have a shift right operation. Because of that, a 0 appears in the first flip-flop because we have J equal to 0 here, and whatever was here gets shifted to the next flip-flop and so on. With one more clock pulse, we have one more shift right and so on. Let us now start with counters. Counters are circuits with several states, and in this picture or the state transition diagram, each state is represented by one circle here. This is state 1, this is state 2, state 3, 4, etc. up to K. And after this state, the counter goes back to state 1. And this kind of counter with K states is called a modulo K or mod K counter. And what is inside a counter? Let us see. A counter can be made with flip-flops, each flip-flop serving as one memory element with two states, 0 or 1. The output of the flip-flop Q can be 0 or 1. And if there are n flip-flops in the counter, we have 2 raised to n possible states, because each flip-flop can have Q equal to 0 or Q equal to 1. And therefore, let's say we have 3 flip-flops, then we can have a maximum of 8 possible states here. So our K can be 8. But we can also exclude some states, and therefore n flip-flops can be used to make a mod K counter with K less than or equal to 2 raised to n. So that is what this picture shows. Inside this counter there are flip-flops, and this Q0, Q1, Q2, etc. are the outputs of those flip-flops. And how does the counter go from one state to the next? For example, from 1 to 2 or 2 to 3. That is done by the clock pulses. So every time there is a clock pulse, the counter will advance by one state from 1 to 2, 2 to 3, 3 to 4, and so on. And this goes on. In addition, a reset facility is also provided, this input here, which can be used to force a certain state to initialize the counter. For example, let's say we have 3 flip-flops inside this counter. So the outputs are Q0, Q1, Q2, and we might want the counter to start in the state 0, 0, 0. So that can be achieved using the reset facility. Now in addition, there is also this box called decoding logic shown over here. We will look at that a little later. Here is an example of a counter. This is the general state transition diagram, and this is our specific counter. And in fact, this is a circuit we have already looked at earlier. So the sequence for this counter is shown over here. If we start off with Q0, Q1, Q2 equal to 0, 0, 0, then this is how it proceeds. And here is a table showing Q0, Q1, Q2. So we have 0, 0, 0 to begin with, that is our state 1, that one. Then we have 1, 1, 0, 1, 1, 0, that is our state 2. Then 1, 1, 1, 1, 1, 1, state 3. Then 0, 1, 1, 0, 1, 1, state 4. Then 1, 0, 1, state 5. And then after that, we come back to 0, 0, 0, back to state 1. That means our last state, this one, is 1, 0, 1. So K here is 5. So it is a modulo 5 or mod 5 counter. Let us now look at this decoding logic. This logic is nothing but some combinatorial circuit suitably designed so as to get some desired outputs here. Could be one or more outputs. Now, since the counter is cycling through K states, these outputs will also be periodic. That is, after K clock cycles, the output at any of these pins is going to repeat. Now, in particular, let us take this example. Let's say we have a mod 8 counter, that means K is 8. That means we have 8 states, 1, 2, 3, 4, 5, 6, 7, 8, and then back to 1. This is our clock signal. Now it should be possible for us to design our decoding logic so as to get this kind of waveform at one of the output pins here, for example the first one. Now this signal X is 1 when the counter is in state 3, otherwise it is 0. And since state 3 comes once in every 8 clock periods, if the clock period is T, this interval is going to be 8 times T. Or in other words, the frequency of this signal X is going to be the clock frequency divided by 8. So let us make that remark. It is possible to have a decoder output, say X, which is 1 only for state I, in this case the third state, and 0 otherwise. So for K clock pulses, we get a single pulse at X, that is, the clock frequency has been divided by K. And for this reason, a mod K counter is also called a divide by K counter. So this counter, for example, would be called a divide by 8 counter. Let us summarize. We looked at some operations related to shift registers and also an application, namely multiplication of two binary numbers. We have seen the functionality of a counter In the next class, we will look at some examples of counters. So see you next time.